So today's problem is an interesting problem in the topic of electromagnetic induction. And it states that here we have, so here we have a wire, okay, and there's a uniform current passing through it of magnitude I, and the current is changing at a rate of di by dt. And it wants us to find the induced magnetic flux phi b through the ring, or I should say the magnetic flux. So we know that the magnetic flux is going to be this closed loop integral of the magnetic flux density times ds. And this right here, we can try to model in simpler terms, okay? So we see that the rectangular coil here is at a distance a from the wire. And we also have this value here, this length of r, and the height of L. So the L, it seems like a square, but in reality, the L could vary. And the way we solve this, right, we know that B is going to be equal to mu naught I by 2 pi r. This is the induced magnetic field because of the current. So what we can do, we can transform this integral here. And the way we do that, say we take some arbitrary value here, and we'll call this lowercase r. And we'll also call this thing right here, we'll call this ds, okay? And ds then, or dr, is going to be that value. It's not a vector. But basically, in principle, we see that ds, this area right here, is going to be equal to L, this value right here, times dr. Okay? And based on that, we can actually transform this integral, because we see that this is also equal to be a whatever, okay? But instead of having just a constant b, we're going to sum it up over smaller rectangles. And therefore, we get the following. So the phi b is going to be equal to the integral of rb mu naught I by 2 pi r times our ds, or our dA, which is going to be L dr. Now we have our integral, and it's in terms of r, so we need to look at what the lower and upper bound for r are. And here, in this case, it's a and a plus uppercase r. So a plus uppercase r. Now, if you look closely here, mu naught I, 2 pi, and L, they're all constants. So when you integrate this, you're going to get mu naught L by 2 pi. And then you're going to get, from this 1 over r, you're going to get log r, which is going to be valued between a plus r and a. So it's going to be log a plus r over a. And this is the magnetic flux density that's going to, or magnetic flux that's going to pass through this. Now, we want to actually find the EMF induced here, okay? So, okay, mu naught IL. And in fact, there's nothing said about the motion of the coil or anything else, okay? We're not going to change AR. That's all constant. So the only thing that's going to be changing, we know, is the di by dt. The I is going to be changing. So we know that the magnitude of EMF induced is going to be equal to d flux b by dt, which is going to be equal to mu naught L by 2 pi times di by dt log 1 plus r by a. And this is going to be the final answer for the EMF induced.